Let's look at another example. Okay, what are some things we might notice here? %, okay.
There's no list.
There's not a list of data. Instead, what we have are. Well, so let's go ahead and start writing down. Well, we have n equals 40, which we're going to definitely be really grateful for, right? Okay, what else? And then this standard deviation, guys, what is it describing? The population or the sample? The sample, so it is an S.
Do you need to have the S of X, or do you just put?
So, knowing that information, what procedure should we use? A one sample t interval for mu, where mu is the true mean NOx level. Nitrogen oxides, duh. Cool, and what conditions need to happen? Is it? Oh, we were given a random sample. Sweet. Normal. N equals 40, which is greater than or equal to 30. Woohoo. Independent. 40 is less than 10% of lightweight engines. Okay, so now how do we get the interval? Stat, arrow over to calc, or stat, arrow over to tests. You're going to choose T interval again, but this time just highlight that what you have is the summary stats. And fill out all the information, yeah? And if the EPA requires that it be 1 or less, how's this company doing? Probably not very good. How do I know? Because the interval is above 1, we can definitely say it's not 1 or less. Yeah. And it's kind of important. Are we feeling okay about these? All right. So tomorrow we're going to do a few of this. Does anybody remember what a matched pairs experimental design was? been a long time. Okay. So like a twin study might be a match pairs design. Or if this singular subject receives both treatments, that was match pairs. And match pairs and then what we did is we randomized the order in which those things were assigned, right? Okay, and so for a match pairs design, the idea was that you ended up with paired data and you looked for the difference between two numbers. Okay, so for example, if you want to test on the effectiveness of a blood pressure medicine and you do a match pairs design with twins, you would take twin A and twin B, give them each one of them the blood pressure medicine, one of them the placebo, and you would directly compare those two numbers. So you like say, the blood pressure medicine was 5 points higher than the other one, or vice versa. Okay, so basically anything where we're looking for a difference between two values for an observation. One observation is the difference between two different numbers. That's what we call paired data. Paired data essentially means each observation is a difference between two numbers. Could be from a match pairs experiment, okay? It could be, for instance, before and after studies. Those would also be paired data, right? So like, let's say that I did a study where I wanted to show whether or not you guys improved. So I had you guys take a pre-test, and I had you guys take a post-test, and I looked at how much your scores improved, right? That's not necessarily a match pairs experiment, but it wouldn't make sense for me to compare your post-test scores to decide if you've improved. I would look at each of you individually and say, how much did each individual improve, right? Okay? So we would take maybe after minus before, and that would give me your improvement score, right? And that would be paired data. Okay, and so anytime you would there's something that connects two data points, and what you're actually looking for is the difference between two individual points, that is paired data. Okay? And to do paired data, you do the exact same thing as you would do for a one sample procedure. So let's look at an example. Oh, look, pre-assessment, post-assessment. All right, so as we look at this one, if I were to ask you for each kid, what was the improvement score, could we do that? What do you think we should do if we want to calculate a improvement score? Subtract. So, and do you guys want to do post minus pre or pre minus post? It doesn't matter, by the way. We just need to decide. Post minus pre. Okay. And so this one would be 2, this one would be 3, this one would be 2. Is everybody good with where these are coming from? All right, now, there's something I want to point out. and I don't do a good job labeling this table. Are you guys cool if I tell you that this was student A, student B, student C, student D, etc.? So the reason I'm allowed to directly compare these two numbers is because they came from the same student. So if we want to do a paired procedure, there has to be some quality that pairs the pre and the post together. In this case, it would be that they're coming from the same student. In a twin study, it would be your twin pairs you to your twin, right? Like, so if Katie and I were in a twin study, Katie's my twin. Yeah. Sorry, Katie's my twin, right? Like, they wouldn't compare me to somebody else. They would compare me to Katie because, you know, our genetics kind of put us together. It's awesome. If I ever need, like, a liver transplant or a kidney transplant, I got a free donor. No question. Pretty great. We actually might be too close genetically. I think that's a thing. Yeah, because whatever causes the issue in one can cause the issue in the other, depending on the cause of the need.
Do you guys have like the same blood type, or is that?
Yeah, we're identical, so genetically we are the same. I'm sorry? Our fingerprints are different, and like our micro DNAs have changed ever so slightly based on our environments because we don't live in the same place. But the like major things are the same. Like she's got curly blonde hair. She's about 5'1". She looks a little bit like me, I suppose. If I were to walk out and she were to walk in, some of you would be able to tell the difference, but not many. If you heard her speak, you would be like, wow, you sound just like Miss Meister. Like when I hear a recording of my own voice, I'm like, when did Katie get here? Katie doesn't know this much about statistics. How could she make this recording? We're pretty identical. You would be able to tell, if we're in the same room, you would be able to tell us apart. But when she first walked in, if she just first walked in, like fooled Mrs. Downer once, definitely fooled Wapner, because she came here, and she was like walking down the street, and someone was like, texted me and said, Meister, why aren't you teaching your 8th period class? And it's because Katie was walking down the street. And they thought I was her. Wait. Is her? They thought I was her. They thought she was me. Is it both? Are they the same thing? Yeah. She's funny. We only talk to each other like 3 times a day, so. It's not 3 times a day, but we do talk to each other just about every day. Also. She's the best. All right, I digressed. You guys want to talk about these some more? Hey, you guys, according to this, did I do a good job? Can you tell me a little bit more about this? What makes you think that I did a good job?
Scores went up.
How do you know that the scores went up? They're all positive. What if I had negative scores? That would suggest I was really bad at teaching. Yeah. Everybody good? Okay. And so let's go ahead and construct and interpret a 95% confidence interval for mu d. So anytime you see construct and interpret, that tells us we're doing boxes. Okay. And so we're going to do, instead of a 1 sample t interval for mu, I'm going to do a paired t interval for mu d, and that d stands for difference, where mu d is the true mean difference of post minus pre-test scores. What do you guys think so far? What do you think we should do next? Check our conditions. Okay, cool. What's the first condition? Random, and is that met?
Yep.
Given random sample. Cool. What about normal? Is that met? Hard to say right now. We would want to see, is the sample relatively mountain-shaped, approximately symmetric, because the sample size, how big does the sample need to be that we don't need to do that? 30. And I don't know about you guys, but I'm pretty sure that 15 is smaller than 30. Pretty sure. Yeah. So, da-da-da-da-da. And are you guys comfortable calling this mostly symmetric? I'm calling that mostly symmetric. Because remember, not just that we draw the graph, we talk about what we're looking for. And then, 15 is less than 10% of Meister students. All right, now what? We've checked our conditions. How do we do these calculations? What do we need to do? Plug those numbers into our list one. And then once we plug them in, run the t. So there is no paired t interval in your calculator. There's just, you run the just like it. That t interval wasn't a one sample t interval. Like anytime you're doing a t interval on a single set of numbers, you use t interval. So once you have it in, you run this exactly like you would do for if this came from a sample, singular sample. And what are we getting? Which means X bar must have been 3.1. 3.13. And S?
0.99.
Are we feeling okay? All right. So then we say we are 95% confident in the interval from So the one thing you would want to be careful here is you would not want to say the true mean test score, because what do these numbers, what did we estimate here? The improvement, like how much the scores went up. Are you guys with me here? Okay, so the true mean, you could say difference between post and pre test scores. Or you could say the mean improvement in test scores would be fine, but you couldn't say the true mean test score because that's not what those are. That's not it's not a test score. The 4 isn't. Like this 4 is not an improvement, or is not a test score. It is the difference between. It's how much the test scores went up. All right, so what about our interval makes us able to say, yep, the scores went up? The entire interval is what, Kira? Positive. What are you guys thinking? Now that you know the basic structures of a confidence interval, are these bad? All right, we're only learning 2 more kinds of confidence intervals. Lots more types of tests, but only 2 more confidence intervals. Cool. This is what I wanted to get through today. So just